Hello everybody. In this video we're going to go over section 10.2, Properties of Liquids. Our learning objectives. First we're going to distinguish between adhesive and cohesive forces. We're going to define viscosity, surface tension, and capillary rise, and we're going to describe the roles of intermolecular attractive forces in each of these properties and phenomena. Remember that in the last section we learned about the different types of intermolecular attractive forces, and eventually we're going to start to use the acronym IMF. So first we'll talk about viscosity. Viscosity is a measure of a liquid's resistance to flow. Okay, so things that don't want to flow have high viscosity. Things that do tend to want to flow have low viscosity. So examples of low viscosity liquids might include water or gasoline or acetone, like the paint thinner. High viscosity liquids are going to include things like honey or motor oil. It is measured in a number of ways. One way is with an electronic device where we have a rotating spindle in a liquid, and we measure the force required to maintain a certain RPM to keep the spindle spinning the same speed. Another way is to measure the amount of time it takes for the liquid to pass through a thin tube. So two examples of these devices, viscometers, are here. Here we have the spindle type, so we're going to rotate the spindle in here. We're going to maintain the speed of that rotation, and we're going to measure how much force it takes in order to do that. And then here we have what you call a free flow viscometer. And basically what you do here is there's like two markings on it, like you might see on a volumetric pipette. You're going to put a bulb up here just like you would on a pipette. You'll draw the liquid up past the first marking, and then you'll let it start to fall with gravity. And then you measure the amount of time it takes between passing from that mark to that mark. The U shape here really achieves two things. Number one, it lets you pick a definite endpoint where it's going to stop, right, once these two levels are equal with one another. And also it keeps you from just having it go down faster due to the extra force of holding up that column beneath it. So it's kind of balancing gravity. Here is a table that you can see in your textbook of some common viscosities, so you can get some sense of what the scale of these different things are. So, you know, honey and motor oil, we can be up into like the hundreds or even up into the tens of thousands, whereas water is going to have a viscosity of less than 1. And viscosity has a unit, and it's some kind of pressure times seconds. Okay, so in this case we have millipascals times seconds. Now we'll talk about the difference between cohesive and adhesive forces. So cohesive forces are attractive forces between identical molecules. Okay, so we have the IMFs from last time, and when those attractive forces happen between molecules that are exactly the same, we call those cohesive forces. Adhesive forces are attractive forces between different molecules. Okay, and I kind of like to think about this because an adhesive would be something like a glue, and I use a glue to stick two different things together. So that's how I kind of remember between cohesive and adhesives. Both of these are a result of intermolecular forces, though. First, we'll talk about a cohesive value, a result of cohesive forces, surface tension. Surface tension is defined as the energy required to increase the surface area of a liquid, or the force required to increase the length of a liquid surface by a given amount. So basically what happens is in the center of a drop, okay, it has these IMF forces that are coming in from every angle, okay, on 3 dimensions. But once you get to the surface, you only have cohesive forces coming from the bottom half, where it's still in contact with the droplet. All right, so to move from the center out to here, we have lost some of those attractive forces. That requires energy, okay? So to move a droplet out and expose more of its surface, we're going to be breaking up more and more of those intermolecular reactions, all of which requires energy. And that's why a liquid is going to tend to form a droplet, okay, that's going to well approximate a sphere and have the maximum amount of internal volume to surface area. The result of this is that a liquid tends to have a sort of skin on the outside of the liquid, all right, and it's going to require extra force to distort the geometry of this surface. This is like one of the classic examples is there's an insect, and basically what it does is it has very thin little legs, okay, and it's able to spread enough of its weight over a wide enough area that it actually won't fall down into the water, but instead just sit on the top, okay, and that's because it isn't applying enough force to break up that surface there and distort it anymore and cause more surface area to be exposed, which is the result of what happens before it would actually fall in, okay? It would dip down, which would distort the surface of the water, creating a little indentation that would have more and more surface area, and then eventually you break through that and you go down into it. But if you never have enough force to get the maximum amount of distortion before the insect's leg would actually come down, it'll just sit on top. Capillary actions. So these are adhesive forces, all right? And what basically happens is there's attractive forces between a liquid and a surface that will cause the liquid to climb up a container or wall or wick up into a material, okay? Here we have a piece of paper towel and some red wine so that you can see it, and basically what happens is that liquid sits down here, it saturates the bottom of the towel, okay, and it wants to move up because it's attracted to the paper towel, and it drags itself up, and every single time it saturates a layer, a few of those molecules want to go up to an area where it hasn't been saturated yet, and it draws it up, okay, and then the cohesive effect is going to cause it to pull up all of its friends further and further up into this material. Capillary rise. So you may not have noticed this is true, but it's certainly true that if you took a thin tube and you stuck it down into water or some other liquid, it will actually come up into the tube and it will saturate the inside of that. And this is a result of adhesive forces as well, okay? So basically what happens is the water is more attracted to the tube than it is to itself, and therefore it's going to be attracted to the walls, and it's going to cause it to climb up it, much like we saw with the paper towel. Now, it could be true, like in the case of mercury, where you have stronger cohesive forces than adhesive forces, and you actually get capillary repulsion, where it's going to push it down into the liquid, and it's not going to want to go inside of the capillary because it would rather stick to itself than stick to the capillary. We have a equation to calculate capillary rise, and you're going to see a problem in the homework and another one in the quiz on this. And basically we have a value of 2. T is our surface tension. We need to be careful with the units on that when we're doing the problem. We have the cosine of theta, which is going to be the angle that we have on the meniscus. We saw that before when we were measuring things, okay? And we know that sometimes it's more pronounced for some liquids than others, so that has an angle associated with it, where if I took the bottom of the meniscus and then drew a tangent line out to where it touched the glass, and then took that angle with the flat surface here, I could measure that. We have R, which is the radius of the capillary tube, rho, which is the density of the liquid, and g, which is a fundamental constant of gravity, the acceleration due to gravity. It's 9.8 meters per second. So this is one where we have to really pay attention to our units. If you look in the homework, I did a whole derivation about this and where we come up with this formula and stuff, and then I did a couple of problems where I go over how we'd handle all the units and stuff when plugging that in. In conclusion, cohesive forces will cause a liquid to attract itself, causing droplets, surface tension, and negative capillary rise. Adhesive forces will cause a liquid to be attracted to surfaces, causing positive capillary rise and the wetting of surfaces. Okay, that's what we would call it when we saw like that wicking up of the thing and up of the paper towel and stuff, or if you saw something that laid really flat on a surface and really spread out as opposed to making like droplets. Both cohesive and adhesive forces are caused by intermolecular forces.